Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to discuss about the module Surface Morphology and we learn about the electron beam lithography part 1 from the paper Characterization of Materials 2. So students, let us see what we are going to learn in this module. First, we will learn about the overview of lithography techniques and we will focus on the electron beam lithography and the working principle of electron beam lithography. So in lithography, the term lithography comes from the Greek words. First is lithos means stone and grapho means write. So low dimensional structures are defined with writing patterns at micro nanometer scale designed by printing text or graphics on the surface of a material, and lithography is currently one of the most feasible techniques used for patterning micro nanoscale features of desired designs with definite shape, size and material compositions, selectively on the material of choice for device fabrication. Several lithographic methods are developed with different resolution, reproducibility, speed, simplicity for processing and acquisition costs, etc. by using different sources of energy. The process of utilizing light source for patterning is termed as photolithography, and utilization of energetic beams as sources are nomenclatured according to the types of energy source. During semiconductor processing, fabrication of micro or nanostructures rearranges the additives by deposition, subtractives by etching and surface dopants by annealing, etching out the unwanted materials and depositing the desired materials for fabrication for a complete nanostructure or device structure is the key concept of microfabrication processing. Lithography is used for defining the wanted and unwanted regions by using a polymer chemical called resist layer over the top of the surface to be patterned. The etching of unwanted material or metallization of new materials are pursued with the pattern resist on the surface, followed by the resist cleaning from the surface of the substrate to fabricate the nanostructured materials or patterns. Simple solvent includes acetone, methyl ethyl ketone, methyl isobutyl ketone for chemicals used for resist, stripping off, lift-off processes. Additional oxygen plasma cleaning is effective for removing residual resist or any organic contaminations during lithography process. Types of lithography. In general, the ability to view or fabricate nano-sized objects depends on availability of strongly focused particle beams. Since diffraction limits the spot size of the exposure, smaller the wavelength of the beam particle produces smaller spots. Here in the tabular are few beam energies correlating to particle wavelength at various energies that decide the spot size are tabulated. The corresponding wavelengths are lambda is equal to 1240 divided by epsilon 0 for photons, and for electrons it's 12.3 divided by E0 plus 10 to the power minus 6 E0 square whole square root, and lambda is equal to 0.28 divided by E0 to the power half for protons. Here few key micro nanofabrication techniques are summarized in the tabular depending on the sources used. In photolithography, photons are the source, and here the minimum feature size we can go up to 1000 nanometer or more. In electron beam lithography, the sources are electron beams with different energies, and we can go up to 10 nanometer feature sizes. In X-ray based lithography, the source is X-ray, and we can go up to 10 nanometer of feature sizes. And finally, in fixed ion beam technique, the sources are gallium ions, and here also we can go up to 10 nanometers. Basic components and working principle of photolithography. Here the energy source modifies the resist dissolution rate. Mask is used that allows patterning by shining direct energy to the resist. An exposure system and aligner is used that aligns the mask to pattern on the wafer. A resist is used that transfers the image from mask to wafer. Schematic of the photolithography technique is demonstrated in figure 1. Generally, photolithography utilizes a light source that illuminates over an area of larger dimension compared to the dimension of the features to be designed. This requires a photo mask of same design with the feature sizes to restrict light to pass through and fall on the photoresist on the substrate. The photo mask is the master pattern of the designs that transfer to wafers. The region where light falls could change the chemical composition of the polymer used as a photoresist and could be dissolved out using another solvent during the lift-off process. The steps for photolithography that is followed is below. First, the sample surface preparation. Second, the resist coating using spin coating technique. Third, pre-bake techniques to soft bake. Then align the photo mask and substrate. Then exposure of the light. Then it goes to post bake or hard bake. Then the development of the photoresist, processing using the resist mask layer, and finally through etching or metallization can be done. And after that we can go for lift-off process where the resist layer is peeled off. The difference between photolithography and E-beam lithography are pointed out in the tabular. The photolithography is a high-speed processing over large area, while E-beam lithography is a high-speed processing for very small area with complex structures. In photolithography, the source is exposed for once and many structures can be defined, while in E-beam lithography, the source is a very small beam of diameter in sub-nanometer region. The structures are defined with point-by-point exposure with a limited speed. In photolithography, the minimum feature size depends on the wavelength of the incident light source. The diffraction of light limits the minimum feature size to be around 100 nanometer at best. But in E-beam lithography, the minimum exposure limit depends on the size of the source beam, no diffraction occurs, and with proper alignment, the resolution of the feature size could go below 10 nanometer. In photolithography, it uses masks to pattern the features, but in E-beam lithography uses computer-assisted program to define the features to be generated. Electron beam lithography is a maskless technology developed in 1950s. The aim is to create nanometer scale structures in the resist that can subsequently be transferred to the substrate material, and the resists used as a patterned mask for semiconductor processing during microfabrication process. The final pattern is created directly from a digital representation on a computer and scanning the electron beam on the resist coated substrate following the computer program. This is pursued with scanning the beam over the resist coated substrate by controlling its deflection from a computer. The exposed regions in case of a positive resist or unexposed regions in case of a negative resist are then selectively removed. Its primary advantage is its ability to draw custom patterns with sub 10 nanometer resolution. This form of maskless lithography has high resolution and low throughput, limiting its usage to photomask fabrication, low volume production of semiconductor devices, and research and development. Example of gold metallization using resist coating and E-beam lithography is sketched in figures 2 to 6. The polymethyl methacrylate, abbreviated as PMMA, as positive E-beam resist with chlorobenzene or anisole as casting solvent is spin coated on the substrate. Electron beam exposure breaks the polymer into fragments that would dissolve in a developer at a ratio of 1:1 for methyl isobutyl ketone and isopropyl alcohol. With the removal of the exposed resist from the substrate, a thin metallic layer is deposited that sticks to the substrate, while on the unexposed areas the metal sticks to the resist surface. After metal deposition, the remaining unexposed resist is dissolved in an aggressive solvent and lift off. The metal sticking to the resist loses footing, and only the metal sticking to the substrate remains after lift off process, and schematized in figure 6. Formation of thin films of resists using spin coating unit. Spin coating is a process used to deposit or coat a liquid or a suspension in the form of a thin film by introducing the solution at the center of the rotating substrate as shown in figure 7. In spin coating, a substrate is placed on the chuck, generally termed as sample holder, of the spin coater that connects to a vacuum pump to hold the substrate. A small amount of resist is poured at the center of the substrate with help of a dropper. Further, this substrate is rotated at a constant angular speed for specific time period. The spinning at high speed using a motor allows the coating material to spread out over the substrate by centrifugal force and is continued till the desired amount of thickness is achieved. The steps to be followed during the spin coating process are indicated in figure 7. Repeating the spin coating process consecutively for few times can form highly thick films. Generally, the spinning speed and spinning time of the substrate are controlled according to the required thickness of the film, viscosity and volatility of solvent, surface tension and amount of solid content in the suspension are additional factors that affect the thickness of the coated film. Centrifugal force, viscous force and evaporation rate of the solvent are the forces involved in the spin coating process. The thickness of the film depends on the viscosity and concentration of the solution. Thinned the films of suspension material can be formed by using low viscous and non-volatile solvents spin coated at higher speeds. Figure 8a and 8b represents the general trend for the expected variation of the film thickness with speed and time as parameters. For most resist material, the final thickness is inversely proportional to the spin speed and spin time. Thickness T is equal to 1 divided by square root of W, where W is the angular speed. Figure 8c shows that for low viscous material, the thickness is low, and for high viscous material, the thickness is high. Electron beam lithography systems can be classified according to both the beam shape and beam deflection. Earlier systems scanned Gaussian shaped beams in a raster fashion. Nowadays, systems use shaped beams which may be deflected to various positions in the writing field, also known as vector scan. An electron beam lithography system, as shown in figure 9, consists of an electron source, a lens system, an electron beam deflection system, a motorized stage, and computers and software to control all the elements. The beam deflection system is used to scan the beam with a writing field, typically 100 micron square up to 1 millimeter square. The movement between writing fields is performed by the motorized stage controlled with a laser interferometer to achieve the smallest possible stitching error between those writing fields. Sources for electron beam. The electrons in metal follow Fermi-Dirac energy distribution. Fe is equal to 1 divided by exponential E minus Ef divided by kT plus 1, where Ef is the Fermi level of the material. The energy required to remove an electron from metal surface into the free space is defined has a work function phi. This energy is provided by applying electric field F and temperature T. It can be written as phi is equal to phi 0 minus alpha T minus square root of E F divided by 4 pi epsilon 0. The techniques for electron emissions from the source material are listed below. Here the types of sources are thermionic emitters, field emitters and photoemitters. First, thermionic emitters. In thermionic emitters, electrons are given thermal energy to overcome the barrier work function of the emitting material. Current is given by Richardson-Dussmann equation, which relates the current density of a thermionic emission to the work function phi 0 and temperature T of the emitting material by a mathematical relation J is equal to 12.4 T square exponential minus phi 0 minus 3.8 into 10 to the power minus 5 square root of F divided by kT, where J is the current density of the emission in millimeter per millimeter square, Kb is the Boltzmann constant and F is the electric field. The second type of emitter is field emitters. It takes the advantage of quantum mechanical properties of electrons. Electrons tunnel out when the surface barrier becomes very narrow. Current for field emitters is given by Fowler-Nordheim equation given as J is equal to 1.5 into 10 to the minus 6 F square divided by phi exponential of 10.4 divided by square root of phi minus 6.44 into 10 to the power 7 divided by F phi to the power 3 by 2. In photoemitters, energy is given to electrons by incident radiation of photons. Only photoelectrons generated close to the surfaces are able to escape from the material. Cathode materials. The thermionic cathodes are generally thoriated tungsten, lanthanum hexaboride, oxide coated, nickel coated, tungsten sponge filled with barium or calcium aluminate are used as sources. In field emission cathodes are generally best but most expensive. Here the emission occurs in lobes because of crystal phases present at the surface, and here the emission can be unstable. Various types of cathode materials used in E-beam lithography are tabulated below. So let us see how we can position this sample on a stage. The scanning of beams is controlled by its deflection from a computer coded program. Exposure in a spot takes 10 to the power minus 7 second, and a mechanical stage is used to move the samples to have a beam exposure along larger distances. Alignment is made for each stage positions either by checking for registration masks or using laser interferometer to precisely measure the stage movement. A good quality substrate for electron beam lithography must satisfy various conditions stated below. First, it should be conductive, or else the wafer would build up an electric charge which would deflect the electron beam, thus distorting the drawn pattern. Second, the base of electronic circuits should be insulating to avoid the entire circuit as short circuited. The substrate should be as close to insulating as possible without distorting the drawn pattern. The most widely used substrate is silicon, which is semiconducting with a thin insulating layer of silicon dioxide on top. Other substrates that can be used are glass plates coated with metal chrome, widely used in mask production, in which the metal layer should be grounded before drawing. The scanning systems for E-beam on the resist coated surfaces. The E-beam scanning system for moving over the resist layer could contain single or multiple beams scanned over the resist layers in vector or raster scanning modes. Various scanning systems are categorized in Figure 10. First, in vector scan, the scanning systems deflect the beam to follow paths dictated by the pattern and is schematized in Figure 11a. A scanning technique where the beam is positioned over an area of the substrate and the features in that area are drawn out using lines according to the pattern data. The beam remains on at all times and the raster scan is performed by following the three steps. First, an area of an individual die is aligned under the electron beam. Second, the beam is deflected so as to draw out the features in that area of the chip. Third, the chip is completed either by a step-by-step and repeat method or by continuously moving the substrate. Here, the alignment of features in adjacent scanning area is also important. A measure of misalignment is termed as the botting error. The second type of scan is called the raster scan. Here, the scanning systems cover the area of pattern by switching the E-beam on and off as required by the pattern's shape and is schematized in Figure 11b. A scanning technique where the beam scans line by line a section of the surface. The beam is turned on or off depending on whether the current pixel is to be exposed or not. The raster scan is performed as follows. The chip is divided into strips of around 2 to the power 8 pixels. The selected strip is written onto the substrate. The beam scans over the substrate line by line. If the current pixel is to be exposed, the beam is on. If the current pixel is not to be exposed, then the beam remains off. The substrate is moved perpendicular to the scan lines by a laser controlled table. So students, let us summarize what we have learned in this module. The advantage of E-beam lithography includes smaller spot size less than 100 angstrom, high speed writing with great precision of E-beam deflection and modulation, good control over the energy and dose delivered to resist, provides an ultimate machine for patterning resist with high resolution, high density, high sensitivity and high reliability. In E-beam lithography, the key force is the quality of the electron optics, that is, the ability to create a focused spot, the choice of resist, substrate and developer, and the process conditions of electron beam energy and dose, the development time and temperature are the key parameters that defines the successful designing of nanometer scale patterns. Two distinct uses of E-beam lithography are: first, direct exposure of resist for device fabrication, and second, the mask fabrication for subsequent photolithography process. Various scanning systems are categorized by the way they scan. The vector scan features two-dimensional full chip scan and provides a distortion-free deflection and uses a stepped stage movement. The raster scan features one-dimensional line scan with continuously moving stage. Thank you.